Hi, today we'll introduce this new topic. It's called the load shear bending diagram. Alright, so in the previous videos, we already understand the concept of internal loading. So this is perfect time to segue to this new brand topic called the load shear bending diagram. So internal loading gets to lead us to this load shear bending diagram. So LSB abbreviation. And I want to say something about this LSB. Load shear bending diagram has been used all the time for structural engineer. Even when you visit a firm who are working on the structure projects, load shear bending diagram is the basic tools they will be using every day in their projects. So it's a very important concept. So now let's talking about what's the difference between internal loading and load shear bending. So if you remember our internal loading, what we could do is we can find the N and V and M, normal shear and bending at a particular point, at a specific point. So how about this load shear bending? What can we get? So for load shear bending, we actually gonna get this internal loading at all points. Okay, so regardless where you cut, we're gonna be able to get expression for it. So which means we're going to get normal and V shear and bending moment as a function of X. So where's the X? For example, you have a beam. It's 1 meter long. And X is defined always to the left as origin. And so in this situation, our X range is from 0 to 1, right? So then if we get expression for all the points between 0 and 1, you got internal loading for every single point. So that's called analytical approach. So today we're going to look at load shear bending diagram, analytical approach. Okay. So knowing that big picture, we're going to use the example to demonstrate how do we solve a load shear bending diagram problem. So this example we're using is simply supported beam, which we have a pin support and we have a roller support. Then we have a concentrated load P right in the middle. Entire length is L, so this is L over 2. Our goal for this problem is to find N and V and M as a function of X, right? Expressed as a function of X. So how do we do that? Let's look at this diagram first. We actually have two sections. Because it's concentrated load right in the middle, then we'll have a section to the left and have a section to the right. If I make my cut, if this is my first cut, if this is my first cut, and I will have left side of this, also have right side of yellow line. Remember, you have a choice to either look at left or right. For this problem, looks like left will be easier. So in that situation, we are going to look at FBD to the left. Then what do we have then? We'll have right? But we need to go back to this entire FBD1 to find our reaction support, and it's give a label then A and B. So at point A, it's a pin support. We'll have AX and AY. For B, we'll just have BY. At this point, I assume you're going to get really quickly by writing down your equilibrium equation. You can even find this in one single step, AX equal to 0, and AY and BY equal because symmetric, and that's equal to half of the P. I'm here going very quickly on this FBD equilibrium because I know you guys have mastered this long time ago. And then we're going to find so we found everything we need for this problem. Then now we're going to go back to our FBD number 2 here, which is the left section. Our AX is equal to 0 and AY is half of the P, right? And how about our internal loading? Follow our sign convention. So N have to be make it tension to be positive. V going to go down to make this entire part going clockwise rotation. Then we have to make a happy smile, M. Then we are going to solve them, okay? So forces at X direction based on FBD number 2 give us N equal to 0. Forces at Y will give us P over 2 going positive upward, and we also have this shear going downward minus V that equals 0. So we got expression for V is P over 2. Then we do moment. We always do moment about where we cut. So in that situation, we have P over 2 for this one times, okay. So pause for a second, thinking about what's the moment of arm here. Okay. Is that a specific point? Did they tell us it's 1 meter away from A? No. This is a random cut. You cut here. But how do we express that then? It's not a specific number. However, it's from here, starting at 0, to where you cut. That cut, it's X. Okay? Because this X is ranging from 0 to 1 here. So that's going to be our moment of arm. So that's difference from what we had before. So it's as a function of X. Okay. And this is make a clockwise rotation, so it's going to be negative. Now let's look at this M. This M you're solving, this internal bending moment, is happen to be counterclockwise, so it's going to be plus. That equals 0. N and V will not show up in the equation because they're going through point where we cut. So that will give us M as expression of P over 2 times X. Okay. So you actually got the expression for the moment. And you also get expression for V, even though there's no X in here. However, it's a constant, right? And you also get expression for N. So what we just achieved is we made a random cut at this point 1 here. Now I want you to think about it. If I were to make another random cut right here to the left of this force P, do you think we're going to get the same results as what you just had over here? If I'm going to make this to be second cut, I mean, will we? The answer is yes. You're going to get the same answer. A quick proof for that. So we have FBD number 3. So what do we have? We're going to go from here to where we cut, so it's going to be extended a little bit longer. If we get the same FBD, we will get the same answer, right? So for this, we will get a y also as P over 2. Then we'll also get internal loading, the bundle we have for the normal and the shear and bending moment. That's still the same. And how about this? How about the moment of arm? That will be x also. This is where you cut. That's going to be a random number you choose. That's going to be x. So you will get the same results as above. Okay? But now let's thinking about it. If I'm going to make a cut over here, it's to the right of this concentrated load P. Will you get the same results? Probably not now. Let's prove that. So you're going to look at FBD number 4. This time, what do we have? We'll have longer beam. This is where we cut. That blue line here. So we will still have our support reaction P over 2. However, what else do we have? We have where this midpoint, we're going to have this force P. That's the difference. We're also going to continue to have this internal loading, normal, shear based on the convention, and moment. So how do we define this distance? That's where you randomly cut. So that's going to be x as well. Okay. So how you already speculate you're going to get different answer. So we need to go back to thinking about it. So this 3 answers you got here, what's the range for x? That's when x is going to be equal between 0 and half L. So if it's in this half, the first half of the beam, you're going to get those 3 results. So here, what you're about to write down, you're solving, is when x is ranging greater than half and less than entire length. Then you are going to get a different function of NVM. So now we're at a crest trying to get those equations. So forces at x will give us n equal to 0. Then forces at y will give P over 2 minus this P, then minus V because they're going downwards. That equals 0. That would give us our V equal to negative P over 2. Okay. Now we're going to do moment about where we cut. So if we do moment where we cut, then first P over 2, the moment of arm will be x, and that's clockwise rotation, so it's negative. Then we'll have this force P. What's the moment of arm? That moment of arm will be the distance from here to where you cut. What's that value? Okay, so think about this from here to here. That's L over 2. And this entire length is x. So this value, the moment of arm, will be x minus L over 2. That's the moment of arm. And that make it counterclockwise rotation, so it's positive. Now, the last thing to add into this equation is going to be our moment you're solving. And this moment happen to be counterclockwise, so it's going to be plus m, that equal to 0. So keep in mind what you're solving here. You are trying to find expression, right? You're trying to find this expression for this moment at any different place you cut. So you're solving for m here. That's you're solving. So m is going to have expression. M is going to be equal to, move this to the right, so it will be p over 2 times x minus p x minus L over 2. That would give us negative p over 2x plus p L over 2. So if you want to simplify, make this a little bit better looking, so it will be p over 2 L minus x. So that's your expression for this m bending moment. And do a little comparison. This bending moment is different from this bending moment. Why so? Because the range is different. This is the second half of the beam. Okay? So, quick recap. What you have done so far is getting expression for normal and shear and moment as a function of x. For this particular problem, this concentrator is right in the middle, so you have left section and you also have right section. So you work them individually to find expression for them. Okay? So if you want to put them together, I can summary. So that's your results here for this problem. When x is the first half of the beam, we got n equal to 0, v as well, p over 2. Our bending moment, go back to this one, it's p over 2 times x. That's our expression. Then when the second half of the beam, you get another set of equations for internal loading, n still equal to 0. V, however, is negative p over 2, and m is p over 2 times L minus x. Okay, so that's the results you have. One last thing to recap everything, to show these results in a visual way, it's going to be our load, shear, bending diagram. So let's start to draw this load, shear, bending diagram. LSB diagram is basically a 3-tier diagram. So I always think about this as a wedding cake. So the first tier is going to be your loading, and second will be your shear, and the last one will be our bending. So the first one load is basically our FBD. So remember, this is a simply supported beam with a concentrated load right in the middle. So the FBD for that will be P right here, and the support reaction at both ends as P over 2, being symmetric. Now for the shear, for this entire beam, we have two sections. The first section is first half of the section. Our shear is P over 2. So it's going to be a constant value, P over 2. However, once you get into the second half, your shear is getting to be negative P over 2. So what happens is you're going to have from this point, you're going to jump down, straight downward, and here we're going to close the ends. That's going to be our shear diagram. this demonstrates for the first half, the shear is P over 2, the second half is negative P over 2. Now let's work on the bending diagram. So you also have two sections. For the first half, we have this expression P times 2 times x. So that will be what? That will be a linear function with slope as P over 2. So when x equal to 0, m, so we can make a note here. So I'm going to go back here. When x equal to 0, when you plug it in, your m is equal to 0. Then when x equal to L over 2, our m is going to be equal to PL over 4. So we know our original point is 0. And when x is equal to L over 2 here, your bending moment is going to be this value, PL over 4. And to connect those 2 points, it's going to be a linear straight line because this is a straight line function and with a slope as P over 2. Okay, so we're done with the first half. Now we're going to move on to figure out the second half. We're going to use the same fashion. Second half, the first point is L over 2, the midpoint. And when we plug x equal to L over 2 into this function, your m is going to be equal to P over 2 times L minus L over 2. That will give us PL over 4. Then let's look at the endpoints. When x is equal to L, m is going to be equal to P over 2 L minus L. That gives us 0. So the initial point will be PL over 4, the same point where it ends at the beginning of the half. Then the last point is going to be 0. And how do we connect those 2 points? Again, this is going to be a linear line, so it's going to be a straight line. Okay, and what would be the slope for this? The slope is decreasing and it's a negative value. The slope based on this equation, you can also tell it's going to be negative P over 2. Okay, so that completes the bending diagram. So this tells us where do we have the maximum bending. So from here, you can find out m. The maximum bending occurs at L over 2, the midpoint for this beam, and the maximum value is PL over 4. That's where you see the maximum bending happens. Okay, and this information is very helpful for engineers because if there's something gonna collapse, likely gonna collapse at midpoint for this particular external loading. Because right there, you have the maximum bending. All right, so that concludes our discussion today about load shear bending diagram. So quick recap. For this particular problem, we understand you can use load shear bending diagram to find the expression for all 3 things, normal shear and bending. Then once you get that, you can express or graph them into this load shear bending diagram. All right, so keep on going and I will see you next time. Bye now.